mentioning within the talk. You can find now newly Blue Sky and Twitter, or go to my website right there to check out my background or whatever, or email me. Of course, if you're interested, get in touch. Okay. I want to make sure I can just see it here. So the basic problem I'll be addressing here is how to convey a human function that's implicitly present in your brain to a machine in an explicit way. So how do we use this, right? Sorry. So normally, let's say I'm part of the photons. My eye to electrical and chemical signals, and they go into my brain. Some magic happens, and then somehow the symbol tortoise kind of pops into my head. I can associate a meaningful label with the array of pixels or whatever that I saw on my retina, right? So there's like this magic in the middle kind of happening, associating this semantically meaningful label with the picture of a tortoise. And I can do this with a bunch of things. I can look at the world and associate semantically meaningful symbols to arrays of kind of meaningless numbers and pixels. And in my head, while doing that, there is an implicitly specified function, f mapping images to semantically meaningful labels, that's kind of performing this task for me. But I don't have an implicit, I don't have a conscious access to the inner workings of such a function. It's kind of learned automatically. My brain can perform this kind of procedure kind of in no time. It's very robust, it's great. But I, as like the conscious self speaking right now, cannot really tell you how I do this mapping x to y using this kind of mysterious function f living inside my brain. Then kind of two humans look at the world in a very similar way. They develop two functions, f1 and f2, in a very similar manner. They agree on the most of things. The functions are likely not exactly the same, but in broadly defined terms, they are kind of in agreement with each other. Now, I would like to teach this function to a machine. So what do? I collect a data set of images and the associated labels, the symbols that carry the semantic meaning, automobile, bird, cat, deer, whatever. And using this dataset and some procedure, such as neural network as a functional approximator and gradient descent as a teaching algorithm and backpropagation to actually update the weights within the network, I try to convey the same function to a machine in this very like roundabout way. And the machine develops a function G, mapping images to labels in some way. And I don't really know, how to compare F and G in a good way. Both of them are good at seeing things. You look at a picture of a dog, you say a dog, a machine looks at a picture of a dog and says a dog as well. But, despite this great similarity in many input points, the two functions are not necessarily the same, and I'll be discussing how exactly different they are in this talk. There are surprising differences between them. They're not the same. Image models are typically extremely robust on average. Like in almost every case that you can expose them to, they agree with the human judgment of what the input image is. And this is interesting. And this gets better with scale. So scaling has been a dominant paradigm in making things better in machine learning recently. The bigger the model, the more neurons, the more compute spent on the training, the better the model is in basically every domain, including the robustness of models. This is a surprising thing. Many people didn't expect the robustness to also go together with accuracy and these kind of like directly optimized for qualities. Image classification, the easy task, associating labels with images is a very easy to measure performance, and models are good at that. You can measure the accuracy of that. But models are also good at responding to OOD inputs. For example, a noised up version of an image, is also triggering the same label in the model, dog, cat, whatever, despite very strong amounts of noise and deformation or augmentation being applied to the image. And we know models are very robust in kind of this regime in which we add kind of these deformations and perturbations to the image. A few years back, I got interested in the question of OOD robustness. And OOD stands for auto-distribution robustness. And I had a very great time collaborating with Jia Ren and Balaji Lakshminarayanan right here, the two of my co-authors, and Jia was joint first author on this paper called Exploring the Limits of Auto-Distribution Detection. The TLDR of the story is that there is a really interesting setup in which you've got one distribution, one set of images and labels called the in distribution. That's the thing the model trains on. You can do whatever you want with the training set of the data set. So here it could be CFAR 10. that you've got a second data set that we call the out distribution that could be, in this particular case, a very obviously different data set called SVHN. These are digits that are cropped from Google Images. And so the task for the model is, given the first set of images that you can do whatever you want with from training set, and known the second data set, at test time, I'll expose you to either a test image of the first or the second data set. And you have to tell me which one is which. Despite never seeing the data sets, any examples of that, even the training set or anything like that. So this is called OOD generalization. And models used to be pretty bad at this. They were good at distinguishing images of things from numbers. That wasn't the problem. These two kinds of images are very different even on the surface level. And you could detect the digit or the image here from each other, for example, using some 2D Fourier analysis and the statistics of the different modes that appear in the images. This would be a very easy task to perform. The harder task that resisted for a long time our machine learning approaches was the near OOD regime. For example, distinguishing CFAR100 from CFAR10. Oh, sorry, this is SVHN. This is the easy part. What was hard? So distinguishing CFAR100 from C10. If you look at it, right, on the surface, they kind of look extremely similar. Also, because they are very low resolution images, so 32 by 32 by 3 channels, so very, very, very low resolution images. And the task here would be, given this data set, the training set of that, again, and I'll show you examples of this or that, tell me which one is which, and basically I'll judge you based on the area of the ROC curve or kind of binary accuracy in this task. And this used to be really hard. So we have two approaches to resolving this. The first one was using a lot of difficult math to bridge the gap between the in distribution you trained on and the out distribution you had to generalize to. And there were papers with like 50-page appendices full of proofs and a lot of kind of like very inspired, but eventually not very powerful mathematical tooling deployed to solve this problem. This I didn't kind of prefer as an approach, primarily due to the difficulty of understanding what's actually going on there. Also, due to my kind of strong belief that I cannot really mathematically characterize what exactly is the difference between the in and out distribution in general. I kind of didn't see how to kind of penetrate that barrier, how to bridge the two things from each other. The second approach was essentially, you take a massive pre-training, kind of containing a lot of information about the world, within which some of the concepts are reused in the in-distribution data set. You train only on that, but the model already knows about a bunch of things about the world. And then you kind of generalize to the OOD situation by the virtue of having seen a lot of things in the world. And this approach I greatly preferred because it's much easier to implement, but also it's much more powerful. It also resembles the way humans kind of work in this regime as well. So it might not follow the procedure of OOD detection, kind of the letter of the law, but rather the spirit of the law. In this particular case, if you give me two data sets, one containing some images and the other that I should kind of distinguish from the original one, I can already deploy my kind of pre-learned knowledge of the world that I collected while growing up, learning how to see the world and getting my visual perception in kind of in working order. So I can already bring into the situation a lot of pre-existing knowledge in deciding what's what and which data set an image belongs to. And so this is basically kind of, you can think about this as like a binary accuracy in classifying, the images into one or the other type. So if you were completely bad at this, kind of like at chance, you would be at like 50%. And until this paper, the best models in the world were roughly at like 86% AURC on this particular hard task of CFAR10 versus CFAR100. And this stood there for a long time as kind of like a very hard benchmark to beat. And the score here was improving by like a percentage point per year. So very slow progression. The human level there didn't exist before I started on this project. So I wrote this GUI and I spent a lot of time kind of labeling images myself to like 10,000 images while listening to music and labeling, distinguishing the two data to get like a human benchmark performance in this. And so actually when I say a human, this is like literally me, this line. I spent a lot of time kind of labeling images of cats and cows and dogs. Also the few other humans, we are roughly within like 0.5% of each other. So this is kind of a pretty good human benchmark on this. And so the TLDR of this paper is that if we take a massive pre-trained model, we can just take the embeddings coming out and we can kind of bridge the gap between the machine performance and the human performance really easily without any kind of complicated math, just by the virtue of scale, kind of helping us with the robust generalization. The model is so good that it already contains a lot of things that can be triggered by the data sets in just the right way. and the feature vectors are extremely meaningful. And we can just do simple stuff like Mahalanobis distance and clustering of the kind of embedding vectors coming up to the model to just distinguish the two data sets from each other. When we made the model slightly bigger, it was like slightly better, and ensemble them made them slightly better still, and the same story holds on. But essentially, the bridging between the previous mathematical approaches and the scaling approaches was the thing that kind of changed the performance from underperforming humans to matching humans on this task. So here the lesson is, scale led to robustness in a very straightforward way, with very little math being added on top. And we even saw some scaling laws being involved in this. Yet classifiers are easily broken by like the most minute changes you can imagine if you just choose the changes well. So that's kind of the flip side of the story. That was a positive success story, but this is a negative data point in the whole kind of narrative I'm trying to build. So let's play a game. And I would need a audience participation, so please don't be shy. What do you see in this picture? Dog, yes. Well, a neural network I trained this morning agrees with you. It's a 99.9% dog. All right. Well, I spoiled it, but this was supposed to be a car. You see, there was supposed to be a white square blocking it, so the punchline is gone. But look, the images are very minutely modified. You see this like colorful haze being added to the picture. Yet to the model here, it looks like a 93% car, a very confusing picture, right? So what's going on here? Well, this is a very well-known thing. This is like not a new thing in this talk. We've known about the existence of this for years now, for a decade, basically. And I can design this very specific noise that I add to the picture called an adversarial attack that is designed to fool the classifier specifically into seeing a different thing that it is supposed to, based on a human kind of ground truth that we implicitly kind of benchmark against. I'm very sorry I didn't have the white square blocking the result of the neural net, but you would for sure have said a dog, right? You don't see a car in this, or does anyone see a car? If you do, you might be a computer. So all right. So this is a well-known phenomenon called adversarial examples, adversarial attacks. And it was described in this pretty famous paper now, explaining and harnessing adversarial examples by Ian Goodfellow and Christian Secretary was on the paper as well. Yeah, so this is the example I give in the paper. This panda, at like 60% ImageNet panda, turns into a extremely confident gibbon, like the most gibbonish gibbon ever, with this specific modification, but pre-multiplied by this very small epsilon. So it's a very small perturbation. And I think in this resolution and kind of color depth, you don't even see that the panda is different at the end, right? And yet it's a gibbon to the model to a very high confidence. So this is a very famous and interesting paper, kind of like poking a hole into the robustness story of neural networks. Great paper. A few more examples from my morning experiments. I've got a ship turning into a car with this modification. Still looks like a ship to me. Low resolution, because it's a small data set. And a dog turning into a car, right, that I used in the previous demonstration. This is a problem that doesn't just apply to tiny models and tiny data sets. These are two blog posts I wrote just after the CLIP model from OpenAI got published kind of 3 years ago or so. So the CLIP model has an image encoder encoding an image into a vector, a text encoder encoding a text into a vector. You compare the two things and you get the semantic similarity of the text and the vector and the image by kind of getting a cosine between the two unit vectors, right? So even that is extremely kind of foolable by tiny pixel level modifications. Even that big model that kind of knows a lot about the world and is very robust to a lot of things. Here's an example of a picture of a dog that the model thinks 90% is a dog. Here I add a label bird, just like a sticker in the thing. The model can read as well as see, so it like responds with bird because it prefers the text over the content of the thing behind. And yet I can add a third kind of layer of additional pixel level perturbations here, and I convince it it's neither a dog or a bird, but it's a frog instead. And the thing at the bottom is, originally a truck with a sticker horse. So no, the model thinks it's mainly a horse, partially a truck. It sees it in the background, but I add a pixel level modification on top that you can really see again. And then it says a dog at the end. So neither a truck or a horse. So these pixel level modifications are extremely powerful at fooling the model and yet very unnoticeable on the pixel level here. So far, so good? Yes?
So, I mean, we as humans, I think you present us as like these very robust machines, right? That sort of are not susceptible to these examples. But I mean, we have much more information than the models, right? Like I observe this image continuously, my eyes jiggle.
Totally agree. Yeah.
Then there is this paper that says that, like, if you show us very quickly the images, we are also susceptible to that. Do you think it's like a?
Yeah, I'll literally mention that paper in the talk later. I agree with you. Like I'm 100% on board. I think you're exactly on the right track.
Right.
Yeah. Thanks. All right. It's literally a slide in the talk. Thanks. All right. Well, this doesn't apply just to small models, and this is a result of my most recent paper that I want to show you. I hope it runs. All right. So this is GPT-4, and I'm asking it, what do you see in this picture? I'll paste the picture into the thing. Look, it's a picture of Stephen Hawking. Look at what the model says. It's a Rickroll for the model. If you don't know what a Rickroll is, it's this like famous music video from the 1980s by Rick Astley called "Never Gonna Give You Up." And people use this as like a link they give to people. Like they say, "Oh, look at this whatever paper," but instead it's a link to this like video. It's like just like a guy dancing and singing from the 1980s. But I designed a picture of Stephen Hawking such that this $100 million model, GPT-4, to which I had no access, obviously, the weights of which I had no access to, is fooled by that picture into seeing a very specific target, not just a music video, but the very specific music video I'm showing here on the screen. So this is it took me like a cent of compute and an open source model alone to design an attack breaks one of the best models in the world in its image perception capacity. This is in my most recent paper. So it's obviously not a problem of just tiny models. Like even the biggest, the most safeguarded, and the most kind of guardrailed models in the world are susceptible to the same thing. And they haven't blocked me yet, so I can still kind of run this as well. So even these extremely powerful near OOD detectors are very brittle. I was very surprised and disappointed when I discovered this, years ago, just like randomly playing with a model. But even if you have a high capacity to tell us if something is in or out distribution, like as I showed you with the previous models, you can still design very small modifications that will flip this decision really easily. Let me show you how. So this picture of the plane here originally was in the CFAR 10 distribution based on the score the model I showed you before assigned to it. It was in this here's like an OD-like score. It was in the red bucket very clearly, right? And then I designed this very specific perturbation, the noise pattern there, that switches the belongingness of the model, of the picture, from in to out distribution in a very convincing way to the model. So you get a picture that was very clearly in distribution, being modified slightly, and now being very clearly out distribution. So despite the ability of the model to kind of tell things apart really easily, you can still directly attack it if you try, into kind of being fooled into believing it's in or out distribution, respectively. So this is a kind of big mark on the hypothesis that scaling will solve adversarial robustness kind of on its own. Despite my best effort or our best effort as a team, as a field as well, to kind of design these very robust OOD detectors, they can still be fooled really easily by designing attacks specifically against that model. So, I just move it from one end to the other. And we actually found a kind of inverse scaling behavior where kind of the bigger and better models were more brittle against this kind of thing, despite their higher OOD capacity. So they were better at distinguishing in and out distribution data sets, and at the same time got worse at being kind of attacked by kind of these specifically designed perturbations. So I think this all kind of goes back to the sheer richness of the input space of the space of all possible images, and we partition that into classes or kind of semantic categories. And I'd like to show you a few examples of what I mean by the extreme amount of kind of richness and capacity you've got in this space. I wrote this mini paper right here, where I try to kind of drive home that point. And I would like to show you a specific example of what can be done. But first, let me tell you roughly what happens here. This is not that surprising, but you can take n images on the input chosen by you and n target labels to which you would like to flip the first one to, the second one to, the third one to. Not the same label. You're not making everything a dog. You're making the first one, let's say, a coffee pot and coffee spot, sorry. And then the second one, an aircraft carrier. The third one, a steel drum, or whatever you want, right? And you can design a single perturbation that when added to each individual picture on the left will produce the change of class on the right. You can pack up to hundreds or even 1,000 images into this single, transformations into a single kind of adversarially designed perturbation that will do the flipping for you. Yes?
So you just choose all the classes you want, you pick each one of them.
Yes.
And then it finds the...
Yes, you can find such a perturbation that will do, basically the game is you give me n image input and n label transform the two signals. And I say, oh, here's the perturbation for you that will do this. A single. Like I was very, very surprised that this works. Like pack into a single noise. It's not like a cat-like, so it makes everything like it's very cat-like when added to this, and a very like aircraft carrier-like when added to that. And it's a very like multi-purpose kind of noise. And so to me, the second perturbation with different amounts as prefactors. And I designed these two perturbations such that if I look at all the images that will be spanned by this, it's like a bunch of slightly modified images in between. They're like biplanes covering this with different amounts of noise in them in two kind of orthogonal directions. And I look at how these images are classified. They spell whatever I want in the space of images. So this is basically a section within the space of possible images, such that in that section, the class laptop spells AGI, and the class turtle spells draws a turtle actually, and the background is the class laptop. So I'm not sure whether this kind of makes sense to you, but I have all the possible images, right? They're like somehow partitioned into classes in this space by the classifier, kind of inducing the classification on them. And I can find a section, a 2D section of this blob such that it does whatever I want. Because there's like so much, different sections available to me that I can choose whatever, basically like whatever you draw here in the 2D map will exist somewhere in that space. So I can kind of reorient the plane anchored at this biplane, at this plane's picture, kind of choosing the rotation as I wish in this like 1,000-dimensional space that will kind of make the cut project whatever classes I want on it. So I hope this makes sense, but it just shows an extreme amount of flexibility I have in the space of partitioning of things into classes. Yes?
If you change the input image, does the structure still stay the same?
No.
It will not basically maybe end up with laptop, turtle, and daisy, but different kind of target words, but basically the structure stays the same? Or?
It'll be completely different. I will have to choose a new perturbation 1 and perturbation 2 to like make that work. But I could design a thing that will satisfy two of these images at the same time. There's like so much flexibility that I can like whatever constraints you give me, like for up to a certain point, I can accommodate them easily. And I was actually like measuring the amount of accommodation I can afford you in this paper, kind of like how much flexibility there is. And I tried to kind of estimate it here in a simple model. So imagine you're like in the space of images, and you're partitioning that space into cells of kind of the same class, right? Like this could be like a class dog and a class cat, and like images in that cell are classified as cat. If you perturb it slightly, you're still within the cell, so you still classified as a cat. So these colors are the classes, and the cells are the regions that are classified as the respective class. What I'm doing here is I take a bunch of these blue dots, those are the original images, and I apply the same vector, the same perturbation to them, and I have to move them to a color that you told me I have to satisfy, right? So I'm starting from like a picture of a dog, and you told me it has to be an aircraft carrier after the perturbation. So this motion has to give me an aircraft carrier color at the end. The same motion has to give me, from a giraffe, like a lion here, or whatever. So like I have to kind of be able to, with the same directional motion, do n different transformations from starting colors to end colors. And in order to accommodate kind of let's say, a maximum amount of images at the same time, while I have C classes to choose from right here, the approximate number of cells surrounding each image has to be roughly that n, just to make that thing I was performing like a roughly probability order 1. And so I can estimate that in this CFAR10 example, there's roughly 10 to the 100 neighboring cells of different classes around each cell containing an image. So there's like a huge amount of neighbors around each point, kind of partially explaining why you can easily find the adversarial attack, right? If you want to move like from a cat to a dog, there's like a lot of dog cells surrounding your cat cell in a very close proximity automatically, because there's like so many of them around you. All right. Well, I think a lot of these things are kind of related to high-dimensional geometry. And here's like a fun blog post I wrote recently where, I won't go into details of, but you get like very unintuitive behaviors in high dimensions, that like you kind of don't expect. And I think there's like a whole class of results called concentration of measure phenomena that both have kind of like blessings and curses of dimensionality in them. Yeah. Let me just go back so I don't spoil it. And they basically like boil down to like some things in high D are much simpler than in low D. For example, Gaussians, become like thin shells of like a particular radius, and that thin shell at this radius containing all the probability mass of the distribution. But some effects become much more complex, like harder to kind of port the intuitions from the low D to high D example. I think a lot of the phenomena that are puzzling in these high dimensional settings are kind of easily explainable by like some like misapplied intuitions from 2D and 3D cases. And I think so what we see here is that these models are robust on average, and yet we can easily find these adversarial attacks that like completely break them. But despite that, like they're like also extremely good at on average at being robust. So like what's going on? And I think the kind of the headline kind of broad conclusion is that it's very normal in high dimensional spaces for things to be statistically extremely rare, as in like the frequency of these things is extremely low. So like the ratio of, let's say, the attacked images that like fool the network to the full number of images is very low, and yet the count of them or their absolute number is very high. So if you try to locate them in that space, you can easily, if you have a guiding light in some way, for example, a gradient taking you to that point, but on average, you would never stumble upon such a thing. So things can be extremely rare, and despite that, extremely abundant in that space. So I think kind of both of these can be the same at the same time true. And I think a lot of the confusion people have around this is kind of stemming from the hard to reconcile kind of 1 and 2. That would be the case in like 2D examples, but in high D examples, these things can be like the case at the same time. So the standard solution to adversarial robustness is not great. So let's say you start from an image here that I labeled with this pretty blob here, and let's say it's a cat, right? But the cells around that image are not cat, but you would like them to be a cat. So like, how do you kind of enforce that to be the case? Well, you attack the image, and then you move to the neighboring cell with a small perturbation onto the image, and you throw that to the data set, back to the training set, and say, oh, you mislabeled that. It's a cat, actually, the perturbed image. So train one more step on that. And then you say, well, can you like, if I like try to sniff out a neighboring image that's also not a cat, could I do that? And you find it, and you say, well, that's also a cat. Like, let me throw that back to the training set. You kind of repeat this procedure of kind of gradually attacking the images, throwing them back to the training set, and repeating that. And this is called adversarial training. It's a very simple procedure. And people have been applying this kind of like at massive scale, even like 1,000 times, more data points coming from that generation of nearby adversarial attacks compared to the training set alone. They throw that back to the training set and they kind of repeat this process and basically manually brute force patch the holes in the classification in the input space. So it's basically a patching procedure. And obviously there are some like redundancies. Let's say patching this cell will also make this cell good. There's like some kind of underlying symmetries being applied to that. So it's not as hopeless as it might sound, given the number of cells around each thing you have to patch manually. But it's kind of semi-hopeless when you increase the resolution of the images and increase the number of classes involved in the problem. Just manually kind of patch these and make it robust by literal kind of commemoration of the failure cases. So in my recent work, I tried to create a more robust image model. And I thought, well, how do I approach this? And I think there's like a lot of approaches to that. And this is not a panacea. This is like not a robust model. This is a more robust model in some regime. And I would like to describe how exactly we go about making that model more robust. And my co-author was Balaji Lakshminarayanan, who was also on the previous paper as well. So the way I try to think about this is like through a kind of a connection between interpretability and robustness. To me, for things to be robust, the changes I induce by attacking the model should be interpretable in the image. So, obviously you can change a picture of a dog into a cat by changing the kind of facial features of the animal from like a dog-like to a cat-like set of facial features. But humans should agree that this is what happened. The non-robustness basically means that you have a mismatch between what humans would say they're looking at and what the model says is looking at. So as long as you've got like interpretability of the changes that happen to the image as a result of the attack, I kind of posit that like you'll get robustness. And some people like have been kind of alluding to this connection historically as well in a bunch of domains. But I think there's like an intimate connection between interpretability and robustness of a model. So that to me is like very encouraging. And so the four kind of like basic elements of this paper are essentially, I would like to ensemble the inputs over multiple resolutions. I would like the model to not look at a fixed single resolution, but rather at a cascade of resolutions at like progressively kind of like lower kind of side size of the image. So there's the first part. The second part is I would like to aggregate predictions over the intermediate layers of the network, and I'll tell you why later. And I would like to use an aggregation procedure that's kind of easy, that has an easy time withstanding an attack that will, for example, drive one logit to a really high value, or like it won't be kind of affected by like an outlier, kind of like just messing up with the aggregation procedure over multiple inputs. And in this paper, as a bonus, we get a procedure that can turn every classifier into a generator for free without training. So that's kind of interesting at the end. I'll show you the pictures. They're pretty convincing. And the attack on the vision LM that I showed you is an example of the result of this paper as well. We kind of flip the difference prior around into an attack prior at the end of the paper. So as you mentioned, right, when your eye looks at things, it jitters around. And I think a lot of people don't know that, but this is a video of an eye looking at a fixed target. And the dot in the colorful field is the center point of the vision field on the retina, right? And the things there are the pixels of the retina, like they're the cone cells and the other cells whose name I forgot. But basically the pixels of the eye. And the eye doesn't really look at straight at a thing, even when you try to focus as much as you can in like looking directly. Obviously, your eye performs other motions. You can deliberately look at a different side, but even without you ever wanting to change the direction, it is moving automatically and it's jittering at a very high frequency all the time. These are called microsaccades. There are also macrosaccades kind of involved in the thing. And in this picture, the microsaccades are like these little tiny kind of motions around, and then the eye sometimes moves a lot and then kind of starts jittering around as well, despite your kind of focus on the particular direction only. So the eye is obviously looking at a thing differently than a model would, right? A model gets like a fixed array of pixels in and makes a decision. Here, the eye kind of looks at a thing moving around a lot and then eventually makes a decision. So it's a very different model. This is my eye, by the way. So I will just move to the next slide. Right. And you mentioned this paper, right? Like just here. So this is a really interesting result. It's very convincing to me. In this paper, they show that so humans are not confused by the dog I showed you. It looks like a cartoon model. But if you expose a human to a extremely short snapshot of the image, let's say 40 to 60 milliseconds, in a controlled lab environment, humans are partially fooled by that image. So humans are susceptible to adversarial attacks the same way machines are, but it has to be an extremely short exposure. It gets corrected really easily after like a few tens of milliseconds like elapse of the exposure to the image. So something about the length of the exposure is kind of like correcting that misclassification due to the attack perturbations. And I think this is a very interesting kind of like and leading point. This has been like this was a great paper. I think doing that is a really valuable kind of comparison between the machine way of seeing and the human way of seeing. And I've got an example of from my own kind of experience. So at home we've got this tortoise here, and it's got this checkered pattern on its shell, right? And I walk around and I try not to step on it because like it would be bad for the tortoise. I like it. I'm trying to be careful, but I'm kind of looking at normal eye level, but kind of glancing at the floor, sometimes observing whether the tortoise isn't like walking around in some way. But we also have this hole at home with a into kind of see the tortoise. Brief exposure also kind of a very different thing than I should be. Obviously, when I look at it later, I kind of get that it's not a tortoise, it's a towel. But this brief exposure also fools me. So this to me was kind of similar in the ephemeral direction of this kind of attack on my visual recognition system. So the way we do this, we take a single picture and downsample it to a bunch of smaller resolutions and stack those into a single multi-channel stack. And so it's a 32 by 32 by 3 image, this one. We make here 4 versions of it, and we stack them in the channel direction. So it's like 32 by 32 by 12 in the end. And we feed the whole thing to the model at once. It's not multiple passes, it's a single pass. And the model kind of, the image goes in from the outside, like this is invisible, so the model does something, but it makes these versions on the inside. These pass into the model and eventually get classified into a class. We found that if you use a high learning rate for training this, it doesn't get adversarially robust. There seems to be some like hysteresis effect going on here. But very low learning rates yielded a model that's relatively adversarially robust when you kind of like, before feeding the thing in, you multiplex the input into similar downsampled and noised up versions of itself. But high training rate didn't lead to that. Low training rate was the key here. So that was a surprising thing. I don't know why this is the case, but empirically we saw that. Now, here's an interesting question that to me is like a very empirically, it's very like science of deep learning type question. And it's basically this. So if I show you the picture of a dog that looks like a car to the model, my question is like, to what extent does the thing look like a car to the model, in the first place? Obviously, the model says it's a car at the end, but my question is like, are the features within the model kind of car-like, or are they dog-like, or are they some third unknown thing? So for example, we know that if you look at a vision model and the things it's sensitive to as the signal propagates through the layers, the early layers are sensitive to textures and like these kind of low-level features. And as you go deeper, you get patterns and parts and objects eventually being the things triggering that specific layer. So the abstraction is being kind of increased as you go through the model. And the question is, on these lower levels of abstraction, is the adversarial attacked image a dog or a car to the model? Eventually it says a car, but are the intermediate layers also saying a car? It turns out it's not the case. Normally, when you kind of read out the intermediate activations and see what the model sees in the intermediate layers, it says it's basically the ground truth from the beginning to the end. But when you attack the image, it only flips the label at the very end of the model. The layers at the beginning and in the middle still see the ground truth class, completely all right. It's only the very end that's confused. So it's a very different kind of confusion than the model would expect if it were actually, a car. And this is just a diagram, but here's a real graph. So here's a layer, and here's probability. And the ground truth class is the green line. So you see that as you go through the model, the ground truth class kind of increases in the probability on this particular data set. This is for normal images. For attacked images that are made to look like the purple class, it's ground truth all the way until the very end, where the ground truth class goes to 0, and the target probability class probability increases kind of drastically. So you see, if you kind of checked in the intermediate layers, it would still answer as the original class. It would only get confused at the very end. But because the readout from the model is only kind of done at the very end, it answers incorrectly. So this is a very interesting phenomenon, right? It's basically non-existent in the early layers. It's only at the very end. And one could kind of do something even kind of like more probing and say, well, if I design the pixels to fool the middle layer to kind of see a car, what would it do in the other layers, right? Like before and after. And it turns out if you kind of attack, let's say here, the image to look like something at layer 27, the accuracy only drops at layer 27 and then recovers after. So the model's layers before and after kind of see to some extent the original class. It's only the layer to which you targeted the perturbation specifically getting kind of confused and layers around it. So there's some like partial decoupling and kind of like unshared, kind of a distinct susceptibility to attacks on the different layers of the model. And so this kind of leads to a pretty like direct idea of like, if the model's layers are partially kind of like distinct in what they're susceptible to, could I aggregate the predictions and make it kind of harder to hit all of them at once, right? I would have to fool all of them to make sure the model is confused. And that's what we do here. So we call this multi-resolution. So there's the input I told you about before. And we call this self-ensemble. So the readouts are kind of like taken from each individual layer using a separately trained linear probe. And these are aggregated at the end into a final prediction right here. So we call this a multi-resolution self-ensemble. And so the idea for why we do this aggregation was this partial decorrelation between the susceptibility of different layers. So multi-resolution, self-ensemble. And so here I'll show you results on a benchmark called Robust Bench, and under a thing called auto attack. It's a suite of in this particular case, 2 attacks being applied in succession. And so the resulting score is, you start from like 80 or 90, and then the model tries to attack. The attack tries to modify the picture such that the model loses its ability to see the correct class. And normally, if you put a standard model in, it drops all the way to 0. It doesn't see anything correctly, right? So the state-of-the-art performance on this particular data set, which is C400, is like 42 or 43%. It takes a lot of compute via this adversarial training I described before to get to that level. It's like a lot of compute. Our backbone, the multi-resolution thing alone, gets to 25% on this data set, on this particular test. So I'm not saying like other tests couldn't be devised to like make it like worse, but on this specific benchmark that people use, it gets to 25%. And when we add the self-ensemble on top, it gets to roughly 46% here, surpassing slightly the state-of-the-art in the field so far, but at 1,000 times or so less compute, because we don't really do any adversarial training. The model itself is that robust without specifically being trained into kind of patching the holes in its classification. And when we kind of do an ensemble of those on top, we get a small additional boost in performance. So this to me was pretty convincing. But it's just a benchmark, so it's kind of hard to see what it means, right? So let me kind of like show you what exactly I mean by the robustness in a more kind of visual sense. You could ask, if I take a derivative of the probability of a class something, cat, let's say, with respect to the image coming in, this gives me the gradient in which I should update the image such that I, let's say, increase the probability, right? So if you do this normally, and follow a few steps on a standard model, you get this, which is a very convincing apple to the model, right? Like that thing, you followed a few gradient steps and you got that. If you do this to our model, you get that. So it actually looks like an apple. So, this would be hard for the model to achieve because it's not steered towards kind of being like visually pleasing apple in any way. It's just that like if you follow the gradient of like the appleness in the image space, you kind of get to that picture really quickly, unlike, with a brittle model. And if you kind of compare this to doing this with a adversarially trained model as were the previously best approaches in this field, you kind of get an apple-like thing right here. But it's a very kind of like, it's a very like diagrammatic apple. It's like much less pretty, if you ask me. But, obviously, even the other robust models that have gotten the robustness through adversarial training have some kind of interpretability in them automatically. So this kind of supports the connection between interpretability and robustness. But I would say our apple is kind of like more visually pleasing. And to me, this is like not a nude statement that is like aesthetic alone. I think it says something about the quality of the gradients that the model provides. The same for the category, for the class girl here. So, this is just noise, but to a model, it's a very convincing girl. This is a girl to the adversarially trained model, and this is a girl to our model without any adversarial training. So this kind of looks like within the bounds of the low resolution, kind of like a female-shaped figure in some way. And if you do this on a bunch of classes, you get like pretty convincingly pretty images if you follow a few gradient steps in that direction directly. And this is not just like a cherry picking. If you repeat this 4 times for these like different classes, you can see, for example, bowl, it's like 4 different bowls. They kind of look like a bowl. So this would be hard to get if the model were just, somehow fooling the benchmark in some way. You kind of get interpretable images out of just following the gradient of the class probability with respect to the image. And today is actually a day in which the GAN paper from 2014 by Ian Goodfellow got the Test of Time award at NeurIPS. I think it was announced today. And these were the images they were generating as like the state of the art at the time for a model specifically designed to generate images, right? This is the result of our model that was never designed at all to generate anything. It was a classifier alone. But we could kind of invert the model in this way because it's so robust that like, you can just say, how should I make a cat, just follow the gradient in that direction and you make a cat or a dinosaur or whatever, dolphin or chimpanzee or chair. So even if you compare it to a specifically designed generative model, obviously with much less compute available, it's like at least a decent comparison. But failure cases still exist. This is like not a 100% foolproof model. And I'll show you a few. So again, participation will be needed. What is this? So what class do you think the model assigns to this? All right. Yes, it's a house. All right. So the house is here, right? Like you kind of see the house-like features there. What is this?
Cloud.
Who says house? All right, who says a road? All right, who says cloud? All right, well, actually, this is amazing because this is adversarially attacked image that got misclassified as a road by the model because this perturbation was added such that it highlighted the road at the bottom, right? So this is a failure of our model. The attack found a perturbation that flipped the label from the ground truth house to a different label road. But because the road was already in the image, it kind of highlighted the road. This, I think, cannot be really considered a failure, but the benchmarks that we kind of use do consider this a failure, a non-robust behavior. And you can see that this attack was being added through a very kind of adaptive way of generating them. So a very strong way of kind of getting the attack on the model. And you kind of highlight it in a very interpretable way, the road, and it got misclassified as a road. Normally, what would happen with a normal model is a noise pattern would be added, and that would be the thing leading to the misclassification. Here, you literally, I'm super happy this happened, actually set a road similar to the model. So it's very aligned with the human kind of way of seeing things. All right, I'll do one more. What is this? So who says sea? All right, who says mountain? Who says cloud? All right, it's the sea. Oh, well, congratulations, you did pretty well. And the sea is here. But what is this? I guess this is kind of unfair because it's blocking a part of the thing. But what do you think this is? Okay, this is like not working as well as I thought. But so it's a mountain, but the mountain was kind of hidden behind the picture, so it's a bit kind of harder to see. But again, I assume like is a very visible mountain in the picture, kind of being added by the perturbation, adding these kind of triangular formations to it in a very kind of interpretable way. It's just like not a noise, right? Like the successful attack was not really an attack. And third time the charm. What is this? Who says horse, dog, cat? All right, it's a cat. It's a cat. Yeah, you're right. And I drew where the cat lies here. When I attack the image using the kind of a very strong adaptive attack, I get this. What is this? Yes, it's a horse. The model kind of fooled the picture into looking like a horse to the model, but even to a human, this kind of looks like a horse, right? It's got like two legs here, the snout.
So bit on the other side, though.
Yeah, I mean, these are very low resolution images, but I'm extremely happy the human perception of the collective audience here is agreeing with the model in what the attack kind of caused to the image. And if you allow the attack to be stronger, you kind of turn a truck into a car in a very interpretable way, right? You kind of see the car forming, right? These are not uninterpretable attacks. Or the cat here turns to a horse in a very kind of easy to see horse-like fashion. All right, well, so the perturbations are very interpretable. For example, here, the pear is being turned into an apple by this line kind of forming here, splitting the pear into a bottom apple and a behind apple. So when the attack succeeds, often it's in a very interpretable way, suggesting the data set itself and the benchmark itself might not be kind of capturing adversarial robustness in the most kind of faithful way. I have a few more kind of bonus things here, and I think I've got time to finish both of them. And one of them is that you can repurpose this multi-scale, multi-resolution approach into a generative prior. You can basically express an image as a set of multi-resolution images from low resolution to high resolution, and attack a model to kind of align its representation with some probability or whatever, simultaneously optimizing all the resolutions at once. Normally, if you do this to a virtual model with a single full resolution kind of template, full resolution perturbation, you would end up with a very noisy pattern here. I'm trying to use a clip model to kind of make this look like a beautiful photo of the University of Cambridge. This to the clip model is that. If I add a bit of jitter, a random noise to the optimization process, I still get a noise that's kind of Cambridge-like to the model. If I add a few more augmentations, for example, kind of jitter in the XY plane, I get slightly Cambridge-like thing. But if I add this kind of prior of multiple resolutions being optimized at once, I get this. It's a very nice picture of Cambridge that came out of a model that was never designed to generate anything. It was a classifier. It was a model that took an image, made a vector out of it. It was never designed as a diffusion model or GAN or anything like that. And yet, by adding this kind of multi-resolution template, a multi-resolution prior into which I'm optimizing, I'm able to extract really beautiful pictures out of it.
Sorry, here the Cambridge photos were in the training set, or
Some Cambridge were, yeah. So it's, yeah. And so, again, comparing what I get from the model that was never trained to do image generation, this is a clip model that I was able to extract from using this prior, compared to the original, I think, GAN paper, you see it's like a huge difference despite the model was never being designed to be a generator. Yes?
So these pictures you get by doing an adversarial attack on your model.
Yes. Oh, no, on a clip model to which I only say the attack is not just a full resolution perturbation. It's like a full resolution perturbation, half resolution perturbation, quarter resolution perturbation, and so on. And I say optimize all these perturbations at once.
So you have several. So your attack must be a sum of all of
Yes. I'm just like flipping it around. Now I don't have to train it in any way. I can just use a pre-trained model and just do that, and it gives me pictures. So that's the magic. In the previous case, I didn't have to do that, but the model had to be trained to be like that, essentially. Yeah, thank you. And yeah, it's quite a, this model looks pretty artistic to me, despite the model not being a generator in any way. So I think this is opening a direction into building a training-free generators out of classifiers, basically unifying the forward pass and the inverse of the model into a single thing. So I'm trying to like work this out right now. If you start from an existing picture and try to modify it into, like, let's say, this Newton into an Albert Einstein picture, normally you would get like a noisy pattern that's very Einstein-like to the model. With this approach, you get this. So you see why the model now thinks it's an Einstein, right? They added like an Einstein hair, Einstein mustache. So this is obviously a picture of Einstein. So you were able to extract human interpretable things out of the model. That was just a generator. And the second kind of side effect is that you can, using this approach, design attacks that fool even GPT-4, Claude, or Gemini, kind of these $100 million order models. Here's the Hawking I showed you before, and here's a turtle that to the model looks like a cannon, that I designed to look like a cannon. All right, here's just like a repeat of that.
but on these smallest, if you do.
Yeah, I kind of have to be,
access to the layers.
I don't have access to the layers. I don't use this multi-layer thing. I just say, I'm basically encoding the cannonness in that picture on resolutions that a model is not sensitive, that the model is sensitive to, but the humans are not. So the model here, the encoder to the GPT-4 likely is just a normal model. And so it only kind of focuses at like one level of abstraction, essentially. And through this kind of approach I described to you, I can use another proxy model to encode the cannon-like information in like in the layer the model is sensitive to, but the other layers still maintain the turtleness. So to a human perceiving all of them at once, it still looks mainly like a turtle, but to the model it looks very strongly like a cannon.
So it works by transfer.
By transfer, yeah. And so this is the first successful transfer of image attacks on vision LLMs, I think, so far. So, we were able to attack Claude, GPT-4, Gemini, Google Lens even. So if you take a picture of that with Google Lens or do Google image search, it would give you a cannon as a thing, similar to that picture. And so I think this is a pretty cool example of a transfer at scale for these attacks. All right, here's, I'm adding more of the perturbation here. So you see that GPT-4 still thinks of Stephen Hawking here. There's the original picture. A bit of, transfer, a bit of information being added, still Stephen Hawking. But here is already enough to kind of flip the decision into, never going to give you up, the Rick Roll thing. And here with a turtle as well, turtle, cannon eventually. So as I'm adding more of the perturbation, at some point it starts being confused by what it's looking at. Okay. Just to summarize, adversarial robustness is, in my view, kind of similarly shaped to kind of AGI alignment to begin with. I'm trying to communicate an implicit function, not human preferences in this case, but kind of human judgment about images into a model. The model kind of agrees with me and the collective humans in the most cases, but you can actively exploit differences that exist and are very kind of stark and catastrophic. Models can be kind of robust on average, yet brittle under attack. So kind of robustness in one sense doesn't mean kind of robustness in the broad sense of the word. This multi-resolution self-ensemble seems to be getting state-of-the-art on these benchmarks. And even under kind of adaptive strong attacks, it still generates kind of realistic interpretable changes. So to me, this kind of suggests not that the model is kind of bad or anything, but like we kind of need rethinking of the benchmarks, because as I showed you, the successful attacks that were performed against this model, if you kind of inspect them kind of in a human way, you see why the labels flip. So that should not be a successful attack for a perfectly designed benchmark. And this multi-resolution prior can be used for both generation out of kind of pre-trained models without any training on top, and also to get attacks on state-of-the-art vision language models such as GPT-4, Claude, or Gemini. All right, thank you very much, and get in touch.